I get a mic check just to make sure you guys are actually hearing me so I don't talk for no reason? All right, Holden is out of commission. Can someone else give me a check, or am I truly not being heard?
Yes, sir. I could hear you, but you broke up.
Okay, that's all right. Yeah, and please let me know, guys, if I break up on something that is important, just ask me to respond. You're not going to hurt my feelings. I would rather spend another 30 seconds saying it again than you guys, end up missing out on a letter grade in the class simply because, 40 other cadets were all watching Netflix at the same time, and so Mission Net couldn't support both that and me teaching class. Okay, so like I said, new 5-day week, but the upside is of all of the times for us to come back to a full week, this was a great one to do it because we don't have a lot of mind-blowing new things to go over. Today we're going to basically take what we did last week with confidence intervals and hypothesis tests, and we're going to just show how to do a slightly different confidence interval and hypothesis test. So the upside is, if last week was starting to make sense to you, today should be an easy transition. Downside is, if last week wasn't making sense, there's no point in going over today. So we're going to start with a review, and please ask questions on it. Same thing with Wednesday and Friday. Wednesday and Friday are going to be two different types of hypothesis tests, both using a new distribution, but the exact same process. Okay, before we go into that, quick reminder, quiz 3 is open now. It is open now until 1700 tomorrow. So anytime between now and 1700 tomorrow, make sure you log on and do the practice and then the full quiz and knock that all out. It is on just lessons 14, 15, 16. So it involves up to confidence intervals, but not hypothesis testing. So get that taken care of. Homeworks 18 and 19 and lab 6 are due Monday. I realize that the homework 18 and 19 are not up yet, but my goal is to remedy that by tomorrow. Lab 6 is up. And I'm hoping now that Kevin Forrest is back and I am not teaching all of them days, I should be starting to get a little bit more ahead. So I'm hoping by the end of this week that I will have all the homeworks and the guided lessons up for the rest of the block, so you guys don't have to keep emailing me passive aggressively going, hey, sir, you know how you wanted us to do stuff? It would be cool if you posted the stuff that you wanted us to do, because that would make it easier to do. Just saying. So that's on me. Like I said, I've been playing catch up here, but I finally got some of my days back, so I am focusing on getting maybe the next several homeworks up. So for those of you who are trying to manage your time and get ahead, that you can have that option to do that. Okay, so with that in mind, anyone got any questions about life, universe, anything, admin, anything I can tell you? Whether or not my wife's birthday went off well, it did. I got her a sous vide machine she was very excited about. Does have the nice side effect that I get to test all of the steak that she's making with sous vide. So, it's really a hard life I lead. Excellent. Okay, so let's do the quick review portion of today. Last week, we talked about a couple of things. One of them was confidence intervals. We had a kind of the big guide lesson. Then I gave you the one slide version. Now I'm going to do the short version where it's the one box version, right? So the confidence interval is when we say, hey, there's a proportion. I don't know what it is, so I'm going to estimate it with p hat. And I do that by taking a sample size of n. I calculate my point estimate. Then I test my central limit theorem conditions, which, as a reminder, these are not the two central limit theorem conditions, right? Those are two parts of one condition, right? These are the two parts of is the sample size big enough? The one I'm not showing here is the are the observations independent? A lot of you guys skip that on lab 5. You got to mention it, either saying here's why it is random sample, or hey, they didn't say it, so I don't know, right? Then we calculate the standard error, we calculate the z-star, and then we go ahead and calculate the interval, right? And I tried to summarize this here of how we do z-star based on the confidence level, right? If I call the confidence level C, meaning if I want 90%, how do I calculate at 90%? Because there still seemed to be, based on some of the homework questions I was getting, some confusion about how we do it, right? So this right here is saying if C equals for a 90% confidence interval, then 1 minus C would be 1 minus 0.9 divided by 2. That would be 0.10 divided by 2, which is 0.05, right? So 1 minus 0.05 would mean that for a 90% confidence interval, I would do Q norm of 0.95, right? And the reason, because visually, very generally, excuse me, is what we're doing is we're saying, hey, I want a 90% confidence interval, which means I need 5% here and 5% here. So to get my Z star of here, I am finding Q norm of 90 plus 5, and that's Q norm of 0.95 for a 90% confidence interval. Now, if I wanted to, some people took a somewhat logical next step of saying, okay, so if for a 90% confidence interval, I say Q norm of 95, that means that for a 95% confidence interval, I want Q norm of 99, kind of just going up. But that's not how it works, right? Because if I want a 95% confidence interval, then what I'm basically saying is that I want 95% here, which means I have 5% split up in the other, which means I have 2.5% here and 2.5% here, which means to find this Z star here, I want 95 plus 2.5, which is 97.5%, which means for a 95% confidence interval, I'm going to do Q norm of 0.975, right? And I can do that for any confidence interval, but you have to do it explicitly. You can't just guess at what it is, right? So that's how we calculate the confidence interval. So questions on confidence intervals in general, because we're going to today say here's how we do a confidence interval for a slightly different thing, but I want to make sure we understand how we do this, or else the other one's not going to make any sense. All right, I'm going to take that resounding silence as deep-seated understanding. Okay, so that was the short version of a confidence interval. Now let's look at the short version of a hypothesis test, right? So a hypothesis test is a little different, right? In a hypothesis test, what we're saying is, hey, I'm going to assume I know what the real parameter P is, and then I'm going to give an alternative option and try to see if there's significant evidence to disprove the null hypothesis, right? So we have this null and alternative hypothesis, and then we define what our significance level is, our alpha, right? We're basically going to say, how strict are we going to be? How hard are we going to make it for ourselves to say that we reject the null hypothesis? Then we take a sample size of n, we calculate our point estimate again, then we test our central limit theorem conditions again, calculate our standard error, we calculate our z-score, right? And so our z-score is different than the z-star, right? So for a z-score, we're saying how many standard errors away from our assumed value is our estimate, right? So that's where this comes from, where we say, hey, take our estimate, subtract off our assumed value, and divide it by the standard error, so we know how many standard errors away it is, right? And then once we have that, then we can calculate our p-value, right? And our p-value is 1 minus p-norm of the z-score that we just calculated times 2 if we're looking for a two-tailed test, meaning all I care about is that it is not equal to the assumed value, or I don't multiply it by 2 if I only care if it is less than or one-tailed, kind of like we did with my brother, where I say, hey, my alternative hypothesis up here was that it was less than P naught or greater than P naught, right? Either way, once I have that P-value, the P-value is telling me the probability that my estimate would have been this far away. And so I say, yeah, did you have a question, Grace? Nope, okay. If the P-value is less than alpha, then I reject the null hypothesis, because I'm basically saying my P-value is too small. It's basically the probability that this would happen is so small that I reject my assumption. I reject the null hypothesis. If my P-value is equal to or greater than alpha, then I say, actually, this probability is high enough that I don't have enough. It's reasonable that this I could have gotten this estimate if the null hypothesis was true. So I don't reject the null hypothesis. So those are my really quick all the steps for a hypothesis test for a single proportion. So before we move on to today, I want to make sure no one has any questions on any of these. Not you can always ask questions later, but what we're about to go through is not going to make nearly as much sense if any parts here don't make sense. So if you have questions, I'm going to pause for an awkward amount of time here for you guys to ask them if you got them. All right, I'm going to say that's adequately awkward. Okay, so if that does make sense, then this should be relatively simple. So that was a confidence interval for a sample proportion. Today we're talking about difference of proportions, right? So to give a real top level view of what we're doing between Wednesday and today is, let's go back to using that example of what's the proportion of men. I keep saying proportion of men. That should be equal opportunity. Let's look at the proportion of women at USAPA, right? So on Wednesday, what we did for what's on the top there is I might ask the question, what is the proportion of women at USAPA? And I could say, hey, I don't know. So I'm going to take a sample and I'm going to build an estimate. And I might say, okay, based on my estimate, I estimate that 30% or the proportion of women at USAPA is 0.3. And then I build a confidence interval around that saying, okay, I think the real proportion of women at USAPA is somewhere between 0.28 and 0.32, right? That's what we did on Wednesday. Today, what we're going to do is now we're going to look at a difference of sample proportions. So I'm going to say, I'm interested in looking at what proportion of USAPA is women, and compare it to what proportion of some other college, I don't know, Yale, is women, right? And so I'm going to ask the question, what is the difference in those proportions, right? What is the difference between the proportion of USAPA that's women and the proportion of Yale that's women? And so if I get an estimate of 0.2, then that means that there is 20%, the proportion of USAPA women is 20% higher than Yale. I'm going to build a interval around that difference, right? The steps are almost identical. Instead of taking one sample, now I'm going to take two samples, N1 and N2, right? Where N1 would be the sample size from USAPA and N2 would be the sample size from Yale. They don't have to be the same, right? I could take 300 from USAPA and 400 from Yale, as long as I keep track of the numbers. Then I'm going to calculate 2 point estimates. I'm going to take my USAPA sample and figure out what proportion of that sample is women. Then I'm going to take the Yale sample and figure out what proportion is women. Then I'm going to test 2 sets of central limit theorem conditions, right? So first I got to say, I still got to check, are the observations independent in each sample? I got to make a statement about that. But then I'm going to say, I'm going to check this for, let's say N1 was USAPA, so I'm checking it for USAPA, and I'm checking it for Yale, so I check all of that. Then I calculate the standard error, but it's the standard error for the difference, right? So it's the standard error for the difference between the two sample proportions, right? But again, if you look at it, you can see the similarities, right? Because it's basically doing the same thing, only here's my fraction for the first sample, we'll call that USAFA, and then here's my fraction for the second one, we'll call that Yale, and I add those up and keep it under the square root, and that is my standard error for the difference. And then once I have that, I calculate my Z-star, which I calculate the exact same way, because remember, the Z-star for a confidence interval is only cares about what the confidence level is, right? It only depends on, am I doing a 90%, a 95%, whatever, right? It doesn't matter, count on anything else, because you can see that and that are exactly the same, right? So I calculate that, and then I go ahead and calculate my interval. It's just now, before the interval was centered around whatever my estimate was, because I said, here's my estimate for the proportion, and then I build an interval around it. Now it's an estimate for the difference between the two proportions, and then my interval around it. So that's it. It is conceptually a little different, but it's the exact same process. It's just now we are trying to build an interval around the estimate of the difference between two proportions, because we're comparing them rather than a single proportion. So questions on how these are different or similar, or what I am doing? Does the idea of a difference of proportions make sense, or is that hurting anyone's head? I saw a question for a second, but maybe it went away. All right, so now we're going to do the same thing, but for hypothesis test. So here is our standard hypothesis test for a single proportion. Now we're going to look at that, but we are going to look at it for a difference of proportion, right? So now we are testing, before we were testing the hypothesis, hey, I assume that the real proportion is equal to some number. Like on Wednesday, right? We said, hey, my brother was accusing me of cheating. And so we were testing the null hypothesis, you know, that the real proportion of sixes was equal to 1/6, right? Now what we're doing is we're going to test the assumption that the difference between the two proportions is 0. And that's always going to be our null hypothesis. We're always going to assume that there is no difference. So going back to our USAFA Yale example, we're basically going to say, hey, our null hypothesis is that the proportion of women at USAFA is the same as the proportion of women at Yale, right? That is our null hypothesis. That is the thing that we are going to be testing, that the two proportions are the same, or another way of saying it, that there is no difference between the two proportions. Then we define our alternative hypothesis, which is either that they are simply, the difference is simply not 0, or if we wanted to go lower or higher, we could just do a one-tailed, right? I could say, I believe that the proportion of women at USAFA is higher than the proportion of women at Yale. And so if I did that, then instead of saying is not equal to 0, I would say is greater than 0, right? Depends on what you are trying to prove or disprove here. Then I define my significance level. What is the standard we're going to hold ourselves to? Is it going to be 0.05, or are we going to make it harder on ourselves or easier, depending on how strict we want to be? Then, just like before, I am now going to take 2 samples of 2 sizes. Then I'm going to calculate 2-point estimates for each one of them. Then I'm going to, for a hypothesis test, here's the new thing we're going to introduce. I have to calculate what's called a pooled proportion. And basically, I'm happy to get into it if anyone wants to set up an EI, and I can go down kind of the rabbit hole of where this comes from. But the basic idea is that I need to be able to calculate this, since I'm comparing 2 different proportions at the same time here. I need to kind of put them together to get an idea of what they would be like if they were in a single population. So if you look at this calculation right here, what it's really doing is it's saying, if we use our example again, it's saying, okay, what if I took my USAFA and my Yale samples and put them all together? If I put them all together into one big sample, what would be the proportion of women in both schools in both those samples, right? Because the denominator is now both the sample sizes. So I am adding up both. And the top, if you look at it, P1 hat times N1, that is the number of women in the first sample, right? Because if N1 is the size of the first sample and P1 hat is the proportion of that sample that's women, then P1 hat times N1, this number right here, that's how many women are in the first sample. And this is how many women are in the second sample. So I'm basically, the numerator is total women in both samples, and the denominator is total people in both samples. And so I am creating this overall pooled proportion of what's the proportion of women across both samples. And if you want to see why we need this, I can show you that later, but it's not as important for you to understand now, but I want to make sure you see where it comes from. So we calculate that P hat pooled, right? Because then we use that in both checking our central limit theorem conditions. We use the P hat pooled to check our if our sizes are big enough, rather than using P hat 1 or P hat 2, we just use P pooled for both. And then when we calculate the standard error, we use the P hat pooled again, right? And so this is similar to what we saw in the confidence interval. It's just I have N1 and N2 here, but across the top here, I just use P hat pooled everywhere. So that's how we calculate our standard error for the hypothesis test. Then we calculate the z-score. Now for the z-score, remember, when we did the z-score before, it was that number up there, right? It was the number of standard errors away that our estimate was from our assumed value, right? So up here, we said, hey, my estimate was P hat. We're assuming it's P naught. So that's the distance away my estimate was. And then I divided it by the standard error to say how many standard errors away my estimate was, right? Well, now I am estimating the difference, right? So my estimate is this right here. It is the difference between my two estimates. And then my assumed difference, I am assuming that the difference is 0. So I'm always going to be subtracting off 0. Obviously, minus 0 doesn't do anything, but I left it on there so you could see what's going on. And so that's where that numerator comes from. It is our estimate of the difference minus what we assume the difference is, and we are always going to assume that there is no difference, that it's 0. And then I divide it by the standard error, so I get my number of standard errors. Then I'm going to calculate my p-value, same way we did before. And then I just compare my p-value, same as before. I look at the p-value and say, hey, if it's less than alpha, then that means the probability that my estimated difference would be this far away from 0 is so small that I don't think it would have happened if the null hypothesis was true. So I reject the null hypothesis. If my p-value is equal to or greater than alpha, then I go, actually, there's a pretty good probability I could have gotten these estimates. And therefore, I don't reject the null hypothesis because it very well could be true. All right, that in a nutshell is all we have for today. That is, it is just the same idea of confidence intervals and hypothesis tests. It's just now, rather than doing it for a single proportion, we are doing it for a difference of between two proportions. So before we look at an example, what questions do you guys have? Because I'm going to start making you do stuff on the next slide. So this is where it would be a good point to ask a question if you're not completely sure about what's going on here. Okay. Well, if you guys are feeling good about it, let's look at this example. And like I was telling in the last class, this is an example that I have good experience with because the question says, hey, in 2018, the United States federal government shut down on December 22nd for 35 days. Now, I don't know if you guys remember this or if you guys care. I remember it quite clearly because I was deployed at Camp Film City in Pristina, Kosovo on December 22nd. And on December 22nd, I was out running and I got a call from my commander back in the United States in Washington, D.C. And he said, he was a 3-star. And he said, hey, Chris, he's like, I'm glad I got a hold of you. Great news. Guess what? It's official. Today you've been promoted to Lieutenant Colonel. We're also proud of you. It's awesome. He's like, when you get back from deployment, we're going to have a big party, but I just wanted to be the first to tell you. And definitely, he's like, hope you brought some extra rank with you. Slap it on, wear it proudly, and I'll see you when you get back. I was like, thank you, sir. That's awesome. So I finished my run before work. I go home. I tear off my major, slap on the new lieutenant colonel, and I go into the office. I'm the only American in my office, and it's a bunch of Germans, Italians, Albanians, Turks, Austrians, and I come in and they're like, hey, Christopher, what is this? And I was like, oh, well, I didn't want to say anything, but actually it's Christopher Sir from now on, but kind of a big deal, blah, blah, blah. Everyone's like, oh, it's great. They buy me coffee, I spend the whole day feeling pretty good. Then around dinner time, I got a second phone call. This one, though, was not from the commander. It was from the commander's executive officer. And she said, hey, funny story. I don't know if you guys have been watching the news over there. Did you see that the United States government shut down? And I said, yeah, I heard something about that. And she goes, great. Anyway, among the things that they didn't get to before the shutdown was Congress left office before they actually officially technically signed your promotion order. So technically speaking, you weren't actually promoted today because they closed before they signed your stuff. So I'm going to have to ask you to put back on that major rank until that becomes official. And we'll let you know when that happens. So I had to go back home, very sadly take off my colonel rank, put back on the major, and then I had to walk back into the office the next day with major rank and see how long it took before each person goes, wait, oh my gosh, what did you do last night? And it was just this idea of like, oh my gosh, the Americans don't mess around. You must have given like one bad briefing and they just tore that sucker right off. And then it took a total of, like it says, 35 days before they opened back up, and then got about a week later got around to signing my order. So I lost about a little over a month of promotion, which when you're deployed is a non-trivial amount of money, the difference between major and lieutenant colonel's deployment pay with everything else. So the point is, I understand this scenario very completely. So it says that a Survey USA poll, which is a company, found that out of 398 Americans who make less than $40,000 a year, 207 said they were affected by the shutdown. The same poll found that out of 216 Americans who make $40,000 or more, 97 of them claimed to be affected by the shutdown. So the question is, they would like us to construct a hypothesis test to determine if there is a difference in shutdown impact between the two income brackets at the 5% significance level, right? So in a big general view, what this is saying, hey, there was this government shutdown. It impacted some people and didn't impact others. And so they took two samples from two different populations. They took a sample from people who made less than $40,000, and they took a sample of people who made more than $40,000 and asked them the same question. And so the question is there a difference in the proportion of how many people were affected in each bracket? So we are definitely doing a hypothesis test of a difference of proportions, because we're not saying, is the proportion of people who were affected equal to this? We're saying, is the proportion of people who made less than $40,000 difference than the proportion of people who made more than $40,000 who were affected? So what to do this, we need to get all of these pieces, right? Some of them are set by the scenario. Some of them we need to calculate in R. So what I would like you guys to do is in the chat, I would like you to start giving me some of these pieces. And I only want you to give, try to give one. So pick one that you think you can do and write it in there. And if you got a question, just speak up and we will talk about it. But as I start to see answers pop up for these, we will talk about what I think about it, and we will switch over to R code if and when we need to. But a lot of things you guys can calculate. This is not everything. We still want to use the prepare, check, calculate, conclude. Like one thing on here is not, I don't have any place to check the conditions, which we would definitely still need to do, but these are the core pieces that we need to calculate. So I would, or not even calculate, like the null hypothesis, that's a sentence, right? Or you could write it as a short equation, but just write in text into the chat as you guys think you got something, or if you don't know where to start, then speak up and we will see what we can get about. But like I said, once you got one contribution in there, then sit back and let some other people, but try to calculate the other parts and see if it matches up with what we got. Okay, so we've got something already. We've got, for the null hypothesis, P1 minus P2 equals 0. So what we're saying is, we're saying P1 minus P2 equals 0. So I agree with that in theory, but for that to make any sense, we do need to define what P1 and P2 represent. So does anyone have any input, either in the chat or want to speak up, about what P1 and P2 represent in our scenario? Or we just start with one. What does P1 represent?
So both P's are going to be proportions of people affected by the shutdown. So what do you want to? It doesn't really matter as long as it's consistent. So I guess P1 is the smaller income bracket, so less than $40,000.
Okay, so we're going to say P1 is the proportion of sub 40K affected, which, like you said, would mean that the other one is P2 is the percent of over 40K affected, right? And I appreciate that we are using P1 and P2, right? Because I've seen before people say P1 hat and P2 hat, but those are our estimates. And the null hypothesis and the alternative hypothesis should always be about the real parameters, right? Because we are making hypotheses or assumptions about the real numbers, and then we use the estimates to make a decision about those real numbers, right? But P1 is the real parameter, the percentage of all people who made less than 40,000 who were affected, right? And same thing, P2 is the true proportion of all people who made over 40,000 who were affected, right? And so here, what we're saying in our null hypothesis is that there is no difference, that the same proportion of each of those populations were affected. Now, this is a small note, but we're not saying that it's the same number of people, because there's a different number of people who make 40,000 and more and 40,000 or less, but we're saying that the same proportion, right? Okay, and then I agree. Jacob says alpha is 5%, right? So alpha is 0.05 because we said at the 5% significance level, right? And the significance level is our alpha. That's the percentage we're going to be checking our p-value at. Okay, so we're saying N1 is 398. So I agree that now, because we have defined what P1 and P2 are, now we can talk about what N1 and N2 is, right? Because N1 would be the size of the sample that we took to estimate P1. So since P1 is the proportion of sub 40,000, then N1 would be the sample size we took of people who made less than 40,000. And up here it says, out of 398 Americans who make less than 40,000, 207 said they were affected. So the entire sample size is 398. So I agree that N1 is 398. And wow, I can't draw or write. And then N2 would be 216 because it says out of 216 who make 40,000 or more, 97 said they're affected. So the total sample size was 216. All right, anyone want to take a stab at the alternative hypothesis? That's what we're still missing on the left side there. If our null hypothesis is that P1 minus P2 equals 0, what is our alternative hypothesis here? Or start filling in the right. We're going to have to come back to the alternative sooner or later, but I don't really care what order we answered in. And like I said, if you're not sure how to fill in one of these blanks, then that would be the time to ask a question. So I'm either looking for answers or a question. I'm equally happy with either. All right. So we've got a possible alternative hypothesis here. We're saying P1 minus P2 not equals 0. So we're going to say P1 minus P2 not equal to 0. And I would agree with that, right? Because it says here in our last sentence, construct a hypothesis test to determine if there is a difference, right? It didn't say construct a test to see if people in the higher income bracket are affected more. It didn't say construct a hypothesis test to see if it was less, right? It just says, is there a difference? So our null is that there is no difference, and our alternative is that there is a difference. It doesn't matter if one's bigger, if P1's bigger than P2 or P2 is bigger than P1. We're just saying our alternative is that they're not equal, that there is a difference. So that would be our alternative. Okay, so Matt, Jacob, and George are out of it for the moment because they've put some stuff in the chat. So I want to start seeing some other answers from other people on the right. So remember, now that we've said what our P1 and our P2 is, and we've said what N1 and N2 is, we should be able to come up with estimates of P1 and P2, right? Because P1 hat is an estimate of P1 based on our sample. P2 hat is an estimate of P2 based on our sample. So those should be relatively easy. Shouldn't even really need a calculator to calculate those. You guys can give me those in fractions just by looking up in there. Okay, so we got go for it.
Oh, my chat isn't working, but I just calculated P hat 1 to be 0.52.
Okay, and that matches with what we got from Grace there. And so I agree with that, right? Because P1 hat is the sample proportion of sub 40,000, which based up on the top there, we said out of 398, 207. So it's 207 out of 398, which equals about, we said that is, we said 0.52, 0.52. And then for P hat 2, that's going to be this 97 out of 216. So 97 out of 216, which equals 0. What we say? 449. I'm lazy. I'm going to call that 4 or 5. And so that is our two estimates. So I agree with Stephen and Grace on that. And then we got a contender for standard error. So now, one thing I'll say on the standard error is I agree you could calculate the standard error for each, right? But remember that because we are doing a difference, we are looking for the single standard error that uses the p-hat pooled. So you're going along the right steps, but we need to calculate the p-hat pooled and then use that to calculate the single standard error. And really, I said before, if you want to talk to me about it, you can, but this is the real reason why we need that p-hat pooled, so we can calculate that single standard error. So with that in mind, what would be our p-hat pooled in this scenario? So if someone wants to throw that up, or I will give, excuse me, Ali, there a chance if you want to see if you can do the p-hat pool. I would greatly appreciate that. .495. All right, and then if you guys want, I'm gonna trust that for the moment. If someone wants to give that a check and give that a thumbs up if you think she is doing well. So I'm going to say, we're going to assume for the moment that this is 0.495, which, I mean, shoot, I could even do that without, that's this up here, right? So I could do that with just a calculator, paper, R. I do all my stuff in R because I am lazy. Okay, so we've got the p-hat pooled. So now we should be able to calculate this standard error. And again, this is where you can definitely do it by hand or calculator, but this is the type of thing that, in my opinion, looks big and ugly, but gets much easier if you plug and chug it into R. So if someone's got R open and wants to give that a try, I would be all for it. And by all means, if people are having trouble tracking and don't have your book open, if you'd like me to flip back so that you can take a look at equations, you are always welcome to say. Okay, we got a point. So, Mario, is that I see a 0.0423. Is that for the standard error, I assume?
Yes, sir.
All right. Someone check on that. Let me know if anyone thinks he's full of garbage or full of correct answers. 0.0423. Okay, now we need a z-star, right? And the z-star is that number of standard errors away that we are, right? So this one is one that's relatively easy to calculate because it should be our estimated difference minus what we assume, which we are assuming the difference is 0, divided by the standard error. So shoot, this is one I can actually pull my weight on, right, with just a regular calculator. I'm not going to try to do public math here. So if I say this is going to be our P1 hat, which we're saying is 0.52, minus P2 hat, which we're saying is 0.45. So that is 0.07 minus 0 is still 0.07, divided by our standard error, which we're saying is 0.0423. And I am getting 0.165 about. Does anyone else get similar values? Anyone want to check me on that? Whoop. 1.65, something like that. All right, now this is the point where at p-value, we're going to have to use R. I mean, I guess you don't have to, You could calculate normal probabilities by hand, but I personally have better things to do with my life. If you guys are like, oh, I have so much free time at USAFA and I need to find some ways to fill it, then awesome, do that. But I would highly suggest you do it in R. So this is a code chunk that after done teaching next period, I'll post it up. But this is the problem we are doing here in the prepare, check, calculate, so we can run through. So here is a lot of the parts that we just defined, right, along with the p-hat pooled. And I can go ahead and run all of that. So much easier to do it here than it is by hand. And you can see, looks like we're getting the same numbers we got over on the right here. My p-hat 1 is 0.52. It looks like everything you guys are doing is checking out. Here's the step we didn't do, where you would have to use that p-hat pooled to check, in addition to saying, yes, the observations are independent because they came from a random sample, we'd have to check these success failure conditions to make sure all those inequalities are greater than 10, which they are. Then we do this big ugly equation for the standard error, right? Which becomes very easy to do in R. And it looks like I don't have to, where did we see? It looks like we don't have to kick Michael out of the class yet because his number looks good for standard error. Then we calculate the z-score and 0.68. I'm going to chalk that up to rounding error because I don't want to get kicked out of the class either. But that is pretty close to the 0.16 that we got before. Here, though, R is keeping track of everything to the last digit, so we're getting some more exact numbers. Then we calculate our p-value, right? And this is where we do the 1 minus p norm. Yeah, Matthew, Matt, what do you got?
Yeah, so going back to z-score really quick, it's maybe kind of insignificant, but so you have p-hat 1 minus p-hat 2, and then minus the, I don't want to say expected value, but the value you expect for that expression.
The expected difference, yeah.
Yes, and that comes from the null hypothesis, correct?
Right. Which I will tell you guys that for the purpose of this class, yes, in the world of statistics, sometimes there is a different null hypothesis when we're looking at the differences. But for this class, if we are doing a difference of proportions, I am always going to have the null hypothesis be that they are the same, that the difference is 0.
Okay, that was my question, is if it's like one is less than the other, then how do you really define that? But
right, so we're not going to worry about that. We're always going to be assuming that the null hypothesis is that they're the same. Then for the alternative, we might say, is our alternative that they are not equal, or is the alternative that one is greater than the other? And so, yes, we might have different alternative hypotheses, but we are always, for this class, going to assume that for the difference of proportions, that the null is that they are the same, or that the difference is 0.
Great, thank you, sir.
Okay, so now I'm going to calculate my p-value down here with my p-norm, and I get a 0.09, and we're doing times 2 here because this is two-tailed, right? Because we said that my alternative is that the difference is not 0. And so the reason that not 0 is two-tailed is that when I look at not 0, another way of writing this would be P1 minus P2 is greater than 0, or that P1 minus P2 is less than 0, right? That is another way of writing that, right? So that's why it's two-tailed, because we're saying if all I care is that they are different, that it's not equal to 0, then I'm saying it's equal to anything besides 0, meaning it's either less than 0 or greater than 0. So I am checking both the tails. And so that's why this is a two-tailed test. And so I do that on the p-value, and I get this 0.09 and some numbers, but I'm just going to call it 0.09. So I'm going to go down here and say 0.09. And so the big, like, anticlimactic end is I say, okay, so my p-value was 0.09, my alpha was 0.05, 0.09 is, if my math is correct, greater greater than 0.05. And so since my p-value is bigger than my alpha, then I fail to reject, right? Which conclusion-wise means that there is not significant evidence that there is a difference, right? So when we look up here, these were our two estimates, and our two estimates were different, right? According to our estimates, we estimated that 52% of the low-income people were affected and 45% of the high income were affected. So according to our estimates, there is a difference, right? But based on our analysis, we said, based on our analysis, our p-value is so big, it's bigger, specifically, it's bigger than our alpha, which was our standard. We're basically saying there is a 9% chance that if the null hypothesis was true and these were equal, there's a 9% chance that I would get these estimates anyway, right? Because I'm showing that there is a 7% difference between my estimates, right? This here is saying, yeah, well, even if there was really no difference, there's still a 9% chance that you would get estimates that shows there's a 7% interest, right? And we're saying 9% is bigger than what we are willing to care about. So I'm saying, yeah, there's not significant evidence to show that there is a difference. And so I fail to reject the null hypothesis. That's our ultimate result. If this p-value had been smaller, then we would have said, if it had been like 0.01, then what we would have been saying is, if there really is no difference, there's only a 1% chance that our estimates would have shown that there is this big a difference. Therefore, I reject the null hypothesis. I don't think they're the same, right? But that's not what happened in this scenario. We got a p-value bigger than alpha. Therefore, there is not significant evidence to show that there is any difference between these proportions. Done. Okay. We got about 1 minute left, so not a lot of time to go in any depth on an answer. I will stick around between this and M3 if anyone has any questions, but if you got to get out of here, get out of here. But if you got a question that you want to just drop it on me now, and I will definitely try to do my best to bring it up on Wednesday. Otherwise, get out of here and work on stuff, and I will see you on Wednesday. So what do you guys got for those of you who want to hang around? If you want to, you're not going to hurt my feelings if you want to leave.
Sir, actually, if anyone else has anything.
Sure.
I had a question going back to the last lab.
Mm-hmm.
So
last lab being lab 4 or lab 5?
Lab 5. So I know they're not graded. I was just kind of curious.
They are graded. I just have to turn them back in today. But they were all graded on Friday. I just haven't hit the turn back yet.
Okay. So I know. So the one that was doing the like the 10,000 simulations of the test scores, it gave the example problem of the die, where you you have basically like just a big for loop, and then the vector you make has basically just 1, 2, 3, 4, 5, 6.
Right. So if you're making a vector, then you're already doing the new one wrong, which is what a lot of people ran into, is that the die example and the example from the on your own portion were different in the fact that the die, every outcome is equal